Hi, this is Justin Zeltzer for Z Statistics. I've got a little video here on regression, and I'm hoping that there's going to be a series of about 5 videos I'll be doing on regression now. This first one is going to be the nuts and bolts, so really looking at the foundations of regression. So if you've not dealt with regression before, I'd say this is a good video to go through, but even if you have, I reckon I come at things from maybe a different angle than you're used to from lectures and textbooks. Kind of make it a little bit more intuitive, so you might find that there's still some stuff in here that is quite useful for you. Anyway, if you can listen in very closely, you might hear it's raining pretty heavily here, so which is quite applicable in a way, because the little sample that I've concocted from the top of my head here is bar takings given the temperature for that particular day. So we've got 9 particular Friday nights that we've sampled out of June and July. We've got the amount of money that the bar has made on those nights and the temperature that was recorded on those days. So I guess the theory is that the greater the temperature, the more likely people will be to go to the pub after they finish on a Friday. If it's a particularly crappy day and it's pretty chilly and overcast, maybe they're just going to go home instead, perhaps. So, if you have a look at the scatter plot that we've got here, we've got our bar takings as the y-axis and the temperature as our x-axis. You can see a positive relationship kind of showing out here, so our theory about the relationship between the takings and temperature seems to be ringing true. But can we be more specific and turn this visual generalization into some kind of equation, some cold hard equation? Or maybe even more importantly, can we assess the strength of that relationship? Those two questions is what regression is all about. Trying to generate a relationship between two variables and then assess the strength of that relationship. Alright, so where to start? Maybe starting from the top is the best place. So the easiest way to think of a regression perhaps is as a line of best fit. So you've dealt with drawing a line of best fit from school days, I imagine. Now that line in statistics is called y hat, which it's a silly name, but we like to put hats on things when they're predictions of true values. So the y hat line is a prediction of y for a given value of x. So for example, at 25, if we have a 25-degree day, we can sort of use this y hat line to assess how much we'd expect to be making from our bar on that particular day. So it's $2,500 maybe, just sort of by sight, having a bit of an estimate there. If it's 15 degrees, you might think it's about what $1,500 we would expect. So it's an estimate or prediction of y for a given value of x. But it's got an equation, which I've written down here, the sample regression line. Minus 353.11 plus 123.54x. So there's a constant term, or a y-intercept, and there's also a gradient of x, or the coefficient of x, which defines y hat. But how do we find those numbers? Where do those numbers come from? I guess intuitively you might think that, well, this y hat line is drawn so that the error terms, the distances to the line itself, is minimized. So if you sum up all those distances to the line's drawn so that that particular value, that sum, is minimized. Well, you'd be correct, but maybe not 100%. The sum of all those raw error terms, if you appreciate what happens when there are positive error terms and negative error terms, I've got the positive ones in blue and negative ones in red. If you sum them all together, you're going to get 0. So that particular summation is not really going to help us find the line of best fit. There's in fact an infinite number of lines you can draw that will have the sum of the error terms being 0. So that's not necessarily going to help us here. What we're going to have to do is actually square these distances. you got to square them to get rid of that negativity. So all the negatives become positive. So on the next little slide here, we'll notice that the sum of the squared errors will be positive, and it's that metric that we're going to be trying to minimize to create y hat. So y hat is perfectly defined as the line that minimizes the sum of the squared errors. So there's only one line that can be drawn that will do that. Now, so it's only for that reason that we come up with all of these sum of squared errors type of things that you might have heard of. SSR, SSE, SST. We only have to square things because of that problem where the negative raw values are going to cancel out with the positive ones. Okay, so now might be a good time to have a look at what SSR, SST, and SSE are all about. So let's do that. Let's have a more in-depth look at these three factors. So let's go back to the beginning, and I'll also draw in here the y bar line. What's y bar? Y bar is the mean value of y. So our bar takings average is drawn in there. Now, what a regression is all about is trying to figure out why a particular variable varies. Why is this particular observation so high? Why on this particular day did we have $3,200 in our pocket, well, in the pub's pocket, and on this particular day we only had, well, what's that one? $800 or something, a very small amount. That's the question. That's what regression's all about. Now, you can assess the deviations here from y bar. So this particular observation up the top here is much higher than the average. The question is, why is that higher than the average? We can separate that distance to the y bar line into an explained deviation and an unexplained deviation. And what I mean by that, here's that y hat line. If you appreciate that this little x that I'm about to draw, so there's that particular point I'm looking at, there's an x. That x represents the expected or predicted value of y for a given value of x. So we're using the maximum temperature to try to refine our estimate for y here. So given the fact that it was 23 degrees on this particular day, we would have expected a higher than average value for that particular day. So x is where we would have expected it to be. So that distance from the x to the y bar line is that expected deviation from the mean. The fact that we know that it was a particularly hot day, for winter that is, means that on that particular day we'd expect it to be higher than the mean, and we'd expect it to be that much higher than the mean. So that's an explained deviation from the mean. There's also now an unexplained deviation from the mean. So despite the fact that we thought it would be higher than average, it was even higher than our expectation. So there's remaining an unexpected deviation from the mean. So out of the total deviation, there's an unexplained component and an explained component. And that's where we start dealing with things like SSR, SSE, and SST. So if you were to sum up all of the total variations squared, you're going to get SST, SS total, sum of squares total. If you sum up just these green bits squared, you're going to get SSR. And if you sum up all of the residuals or errors squared, you'll get SSE. So you'll notice that SST, the total deviation, is equal to SSR plus SSE, which kind of makes sense. That total deviation to the mean is split into the explained and unexplained components. It's maybe a little bit more complicated than that, but that'll do. I think that's a good little visualization as to what SST, SSR, and SSE is all about. We then jump into this thing called R squared, which I think we'll delve more into in the next video, but let's have a quick discussion of R squared. Appreciate that when, I'll go to the next slide here, when the observations are scattered quite randomly, you're going to get a low R squared. Now, what R squared is the proportion of the total variation which is being explained. So if I go back just one slide for a second, you can see it's SSR on SST. So it's the proportion of the total sum of squares being taken up by SSR. So if SSE is quite small, so if these error terms are quite small, your R squared is going to be quite high, because SSR is pretty much the entirety of the total sum of squares. So going back, an example like the one on the left will have a particularly high sum of squared errors. You can see those error terms are quite large here. Huge error terms all over the place. So they'll have a low R squared, the one on the left. The one on the right has a particularly high R squared with a low SSE. So the low sum of squared errors gives you a high R squared. So R squared gives you some kind of indication of the fit of that model. Okay, so with that out of the way, SST, SSR, and SSE, and also R squared, let's now talk about error terms, because I know that there's a bit of confusion around what the sort of lowercase e and the sort of uppercase curly e is all about. So what I thought I'd do is, again, go back to the beginning here and appreciate that the initial sample that we took was an estimate, or the line of best fit that we drew is an estimate of the true relationship between bar takings and temperature. So if we took 9 new observations, so say the next 9 Fridays at the pub, here we go, we've gone from August to September now, we're going to get a completely different regression line. So here you can see that the constant term changed, as did the slope coefficient. Now, what both of these samples are doing are trying to estimate the true effect of temperature on bar takings. So it underpins regression itself, this assumption that there is a true relationship that we can estimate. And it's given by this little equation. It's called the population regression function. Y equals beta naught plus beta 1x plus this curly error term. Now the idea is we can never know what beta naught and beta 1 actually is. We can never know what they are, but we can estimate them. So in this particular estimate, we have 586 as our estimate for beta naught, and that's often termed beta naught hat. This is therefore termed beta 1 hat, or alternatively, you can use lowercase b naught and lowercase b 1. But this is just an estimate of the true relationship. Now, I've drawn the true relationship here as a sort of very godly, glowing line here for that very reason that you can never know where it is exactly, but the theory is that it does exist, and we're trying to estimate it. So what is this curly error term then? That's sort of tacked onto the end of this. What that means is that every observation has some kind of distance, a theoretical distance, to that population regression function. We can never calculate that curly error term, but it does exist in theory. So that's completely different to the original error terms we were dealing with, lowercase e. That's the distance to our sample regression line. And we can calculate that. We actually can find each individual error term. So we can minimize the sum of those error terms squared, whereas we can never know what those curly error terms are. That just exists in theory. And for a given sample, the sum of those curly error terms aren't necessarily going to be 0. So that's hopefully given you some indication of the differences there between the two different errors that you see coming up in statistics. The curly error term and that sort of sample error, which is the lowercase e. So that's it. That pretty much concludes this first video. Hopefully you've found it relatively informative. The next video I'm going to do is going to be quite a good one on degrees of freedom, which I know people have lots of problems with. So stay tuned for that. That'll be a goodie. But thanks for watching.